Launch Vehicle Mark III, LVM3. The Launch Vehicle Mark III or LVM3, previously referred as the Geosynchronous Satellite Launch Vehicle Mark III, GSLV Mark III, is a three-stage medium-lift launch vehicle developed by the Indian Space Research Organisation, ISRO. ISRO changed the name of GSLV Mark III to LVM3 after the successful launch of LVM3 M2 mission. The rename was done to remove any ambiguity on the ability of the vehicle to put payloads in a particular orbit. Primarily designed to launch communication satellites into geostationary orbit, it is also due to launch crewed missions under the Indian Human Spaceflight Programme, or the Gaganyaan program. LVM3 has a higher payload capacity than its predecessor, GSLV. After several delays and a suborbital LVM3 test flight on December 18, 2014, ISRO successfully conducted the first orbital test launch of LVM3 on June 5, 2017 from the Satish Dhawan Space Center, SDSC. The total development cost of the LVM3 project was 2,962.78 crore Indian rupees, equivalent to 45 billion Indian rupees or $530 million in 2023. In June 2018, the Union Cabinet approved 4,338 crore Indian rupees, equivalent to 58 billion Indian rupees or $690 million in 2023, to build 10 LVM3 rockets over a 5-year period. The LVM3 has launched the Crew Module Atmospheric Re-entry Experiment, CARE, India's Space Capsule Recovery Experiment Module, Chandrayaan-2 and Chandrayaan-3, India's second and third lunar missions, and will be used to carry Gaganyaan, the first crewed mission under Indian Human Spaceflight Programme. In March 2022, a UK-based global communication satellite provider OneWeb entered into an agreement with ISRO to launch OneWeb satellites aboard the LVM3 along with the Polar Satellite Launch Vehicle, PSLV, due to the launch services from Roscosmos being cut off, caused by the Russian invasion of Ukraine. The first launch took place on October 22, 2022, injecting 36 satellites into low Earth orbit, LEO. ISRO initially planned 2 launcher families, the Polar Satellite Launch Vehicle for low Earth orbit and polar launches and the larger Geosynchronous Satellite Launch Vehicle, GSLV, for payloads to geostationary transfer orbit, GTO. The vehicle was reconceptualized as a more powerful launcher as the ISRO mandate changed. This increase in size allowed the launch of heavier communication and multipurpose satellites, human rating to launch crewed missions, and future interplanetary exploration. Development of the LVM3 began in the early 2000s, with the first launch planned for 2009 to 2010. The failure of GSLV-D3 in 2010, where the first indigenous cryogenic upper stage, CUS, was flight tested, impacted the C-25 stage program due to the priority assigned for the additional investigation tests and added qualification tests demanded on CUS engine systems. Thus, the unsuccessful launch of GSLV-D3, due to failure in the cryogenic upper stage, delayed the whole LVM3 development program. The LVM3, although named GSLV Mark III during development, features different systems and components from the GSLV Mark II. To manufacture the LVM3 in so-called public-private partnership (PPP) mode, ISRO and New Space India Limited (NSAL) have started working on the project. To investigate possible PPP partnership opportunities for LVM3 production through the Indian private sector, NSAL has hired IFCL Projects Limited, IPL. On Friday, May 10, 2024, NSAL released a request for qualification, RFQ, inviting responses from private partners for the large-scale production of LVM3 rocket. Plans call for a 14-year partnership between ISRO and the chosen commercial entity. The private partner is expected to be able to produce 4 to 6 LVM3 rockets annually over the following 12 years, with the first 2 years serving as the development phase for the transfer of technology and know-how. The first stage consists of 2 S-200 solid motors, also known as large solid boosters, LSBs, attached to the core stage. Each booster is 3.2 meters, 10 feet, wide, 25 meters, 82 feet, long, and carries 207 metric tons, 456,000 pounds, of hydroxyl-terminated polybutadiene, HTPB, based propellant in 3 segments with casings made out of M250 Mar-aging steel. The head-end segment contains 27,100 kilograms, 59,745 pounds, of propellant. The middle segment contains 97,380 kilograms, 214,686 pounds, and the nozzle end segment is loaded with 82,210 kilograms, 181,242 pounds, of propellants. It is the largest solid fuel booster, SRB, after the SLS SRBs, the Space Shuttle SRBs and the Ariane 5 SRBs. The flex nozzles can be vectored up to plus or minus 8 degrees by electrohydraulic actuators with a capacity of 294 kilonewtons, 66,000 pounds force, using hydropneumatic pistons operating in blowdown mode by high-pressure oil and nitrogen. They are used for vehicle control during the initial ascent phase. The hydraulic fluid for operating these actuators is stored in an externally mounted cylindrical tank at the base of each booster. These boosters burn for 130 seconds and produce an average thrust of 3,578.2 kilonewtons, 804,400 pounds force, and a peak thrust of 5,150 kilonewtons, 1,160,000 pounds force, each. The simultaneous separation from core stage occurs at T+149 seconds in a normal flight and is initiated using pyrotechnic separation devices and 6 small solid fuel jettison motors located in the nose and aft segments of the boosters. The first static fire test of the S-200 solid rocket booster, ST-01, was conducted on January 24, 2010. The booster fired for 130 seconds and had nominal performance throughout the burn. It generated a peak thrust of about 4,900 kilonewtons, 1,100,000 pounds force. A second static fire test, ST-02, was conducted on September 4, 2011. The booster fired for 140 seconds and again had nominal performance through the test. A third test, ST-03, was conducted on June 14, 2015 to validate the changes from the suborbital test flight data. The second stage, designated L110, is a liquid-fueled stage that is 21 meters, 69 feet, tall and 4 meters, 13 feet, wide, and contains 110 metric tons, 240,000 pounds, of UDMH, unsymmetrical dimethylhydrazine, and nitrogen tetroxide, N2O4. L110 is powered by 2 Vickers 2 engines, each generating 766 kilonewtons, 172,000 pounds force, thrust, giving a total thrust of 1,532 kilonewtons, 344,000 pounds force. The L110 is the first clustered liquid-fueled engine designed in India. The Vickers engines uses regenerative cooling, providing improved weight and specific impulse compared to earlier Indian rockets. Each Vickers engine can be individually gimbaled to control vehicle pitch, yaw, and roll control. The L110 core stage ignites 114 seconds after liftoff and burns for 203 seconds. Since the L110 stage is airlit, its engines need shielding during flight from the exhaust of the operating S-200 boosters and reverse flow of gases by a nozzle closure system, which is jettisoned prior to L110 ignition. ISRO conducted the first static test of the L110 stage at its Liquid Propulsion Systems Center, LPSC, test facility at Mahendragiri, Tamil Nadu on March 5, 2010. The test was planned to last 200 seconds, but was terminated at 150 seconds after a leakage in a control system was detected. A second static fire test for the full duration was conducted on September 8, 2010. The cryogenic upper stage, designated C-25, is 4 meters, 13 feet, in diameter and 13.5 meters, 44 feet, long, and contains 28 metric tons, 62,000 pounds, of propellant liquid oxygen, LOX, and liquid hydrogen, LH2, pressurized by helium stored in submerged bottles. It is powered by a single CE-20 engine, producing 200 kilonewtons, 45,000 pounds force, of thrust. CE-20 is the first cryogenic engine developed by India which uses a gas generator, as compared to the staged combustion engines used in GSLV. In LVM3 M3 mission, a new white-colored C-25 upper stage was introduced which has more environmental-friendly manufacturing processes, better insulation properties and the use of lightweight materials. The upper stage also houses the flight computers and redundant strap-down inertial navigation system (INS) of the launch vehicle in its equipment bay. The digital control system of the launcher uses closed-loop guidance throughout the flight to ensure accurate injections of satellites into the target orbit. Communication system of the launch vehicle consists of an S-band system for telemetry downlink and a C-band transponder that allows for radar tracking and preliminary orbit determination are also mounted on the C-25. The communications link is also used for range safety and flight termination that uses a dedicated system that is located on all stages of the vehicle and features separate avionics. The first static fire test of the C-25 cryogenic stage was conducted on January 25, 2017 at the ISRO Propulsion Complex, IPRC, facility at Mahendragiri, Tamil Nadu. The stage fired for a duration of 50 seconds and performed nominally. A second static fire test for the full in-flight duration of 640 seconds was completed on February 17, 2017. This test demonstrated consistency in engine performance along with its subsystems, including the thrust chamber, gas generator, turbopumps and control components for the full duration. The carbon fiber reinforced polymer plastic, CFRP, composite payload fairing has a diameter of 5 meters, 16 feet, a height of 10.75 meters, 35.3 feet, and a payload volume of 110 cubic meters, 3,900 cubic feet. It is manufactured by Coimbatore-based LMW Advanced Technology Center. After the first flight of the rocket with CARE module, the payload fairing was modified to an ogive shape, and the S-200 booster nose cones and intertank structure were redesigned to have better aerodynamic performance. The vehicle features a large fairing with a 5-meter diameter to provide sufficient space even to large satellites and spacecraft. Separation of fairing in a nominal flight scenario occurs at approximately t+253 seconds and is accomplished by a linear piston cylinder separation and jettisoning mechanism, zip cord, spanning the full length of payload fairing which is pyrotechnically initiated. The gas pressure generated by the zip cord expands a rubber below that pushes the piston and cylinder apart, pushing the payload fairing halves laterally away from the launcher. The fairing is made of aluminum alloy featuring acoustic absorption blankets. While the LVM3 is being human-rated for Gaganyaan project, the rocket was always designed with potential human spaceflight applications in consideration. The maximum acceleration during ascent phase of flight was limited to 4G for crew comfort and a 5-meter, 16-foot, diameter payload fairing was used to be able to accommodate large modules like space station segments. Furthermore, a number of changes to make safety-critical subsystems reliable are planned for lower operating margins, redundancy, stringent qualification requirements, revaluation, and strengthening of components. Avionics improvement will incorporate a quad-redundant navigation and guidance computer, NGC, dual-chain telemetry and telecommand processor, TTCP, and an integrated health monitoring system, LVMH Group's R&D arm, LVMH Recherche, and the biotechnology company Integrated Biosciences. The launch vehicle will have the high-thrust Vicus engines, HTVE, of L110 core stage operating at a chamber pressure of 58.5 bar instead of 62 bar. Human-rated S-200, HS-200, boosters will operate at chamber pressure of 55.5 bar instead of 58.8 bar and its segment joints will have 3 O-rings each. Electromechanical actuators and digital stage controllers will be employed in HS-200, L110, and C-25 stages. The L110 core stage in the LVM3 is planned to be replaced by the SC-120, a Keralox stage powered by the SE-2000 engine to increase its payload capacity to 7.5 metric tons, 17,000 pounds, to geostationary transfer orbit, GTO. The SCE-200 uses kerosene instead of UDMH, unsymmetrical dimethylhydrazine, as fuel and has a thrust of around 200 metric tons, 440,925 pounds. For such engines can be clustered in a rocket without strap-on boosters to deliver up to 10 metric tons, 22,000 pounds, to GTO. The first propellant tank for the SC-120 was delivered in October 2021 by Hindustan Aeronautics Limited, HAL. The SC-120 powered version of LVM3 will not be used for the crewed mission of the Gaganyaan spacecraft. In September 2019, in an interview by Astrotalk UK, S. Somanath, director of Vikram Sarabhai Space Centre, VSSC, claimed that the SE-2000 engine was ready to begin testing. As per an agreement between India and Ukraine signed in 2005, Ukraine was expected to test components of the SE-2000 engine, so an upgraded version of the LVM3 was not expected before 2022. The SE-2000 engine is reported to be based on the Ukrainian RD-810, which is itself proposed for use on the Mayak family of launch vehicles. In 2025, Russia has also offered to integrate the RD-191M engine on future variants of the LVM3. The C-25 stage with nearly 25 metric tons, 55,000 pounds, propellant load will be replaced by the C-32, with a higher propellant load of 32 metric tons, 71,000 pounds. The C-32 stage will be restartable and with upgraded CE-20 engine. Total mass of avionics will be brought down by using miniaturized components. On November 30, 2020, Hindustan Aeronautics Limited delivered an aluminium alloy-based cryogenic tank to ISRO. The tank has a capacity of 5,755 kilograms, 12,688 pounds of fuel, and a volume of 89 cubic meters, 3,100 cubic feet. On November 9, 2022, CE-20 cryogenic engine of upper stage was tested with an uprated thrust regime of 21.8 metric tons, 48,061 pounds. Along a suitable stage with additional propellant loading, this could increase payload capacity of LVM3 to GTO by up to 450 kilograms, 990 pounds. On December 23, 2022, CE-20 engine E9 was hot tested for a duration of 650 seconds. For the first 40 seconds of the test, the engine was operated at 20.2 metric tons thrust level. After this engine was operated at 20 metric tons, 44,092.5 pounds, off nominal zones, and then for 435 seconds it was operated at 22.2 metric tons, 48,942.6 pounds, thrust level. With this test, the E9 cryogenic engine has been qualified for induction in flight. It is hoped that after introduction of this stage, GTO payload capacity can be raised to 6 metric tons, 13,228 pounds. LVM3 has accumulated a total of 9 launches, as of December 24, 2025. Of these, all 9 have been successful, giving it a cumulative success rate of 100%.